As another example, if we consider an inclined plane with an object on it, and then if it's slipping, then what is the acceleration with which it's slipping down? So we make the free body diagram. The first force is the weight, mg, which acts vertically down. The normal force, which acts perpendicular to the surface, the normal force. Since it's tending to slide down, there will be a friction force backwards. And well, these are the three forces. Now if we set up the xy coordinate system like this, with x horizontal and y vertically upwards, then it would be relatively hard to solve because we have two forces which are not in the x and y directions. So instead of using this coordinate system, it's better to use a coordinate system where the x is along parallel to the surface, that's x, and y is perpendicular to the surface. And well, this would be negative x and this would be negative y. So now y, the normal is parallel to y and f is parallel to x, so we need to break up the mg. So we'll make the force in the y direction, we'll make that with a red color. So this normal will be in the y direction, and this will have a component mg cos theta in the negative y direction. And in the x direction, if we use blue color, then this will be mg sine theta. So we break up the mg into mg cos theta and mg sine theta. You could draw this here, or you could draw this here also. And then we also have the friction in the x direction, which is backwards. And now we write the sum of forces. Normally we first write the sum of forces in the y direction, and it's not going to move up or down, so it's going to be 0, and that's going to be normal minus mg cos theta, negative because it's in the minus y direction, equals 0. So the normal force equals mg cos theta. And now we write the sum of forces in the x direction, and it will have an acceleration. Let's assume that its static friction is not so large, so it's going to accelerate downwards, and this is going to be max. And in the x direction we have mg sine theta in the positive x minus friction in the negative x equals max, and the friction is mu n. In this case, if it is sliding down, it's mu kinetic, and that's the normal force, so this is going to be mu mg cos theta. So that's the friction. We use the known values here to get the friction, plug it in here, and we can get the value of ax. Now, well, with the numbers, it can be solved. Now let's do one last example, which is a rough surface here, horizontal, and there is a pulley here which is supported here, and there's a string and an object over here, and the string goes down here, so it's the same string going over, and there's a weight over here. This is m1, this is m2, and there is a force pulling it at an angle theta. And now we want to see what's going to happen. So let's assume this force is large enough that it's going to pull this to the right, so this will be pulled upwards. So this is what's given. Now we need to set up the free body diagram. So again, we can set up the x and y here as parallel to the surface and perpendicular to the surface, which also happens to be horizontal and vertical. Then in the x direction, we have fx, and we have tension. So the tension is going to pull backwards, and if there is friction and if things is going to the right, we have friction. And in the y direction, we'll have fy, and we'll have mg, and we will have the normal force. Okay, so these are all the forces that we will have in the x, and 3 in the y, 3 in the x. Now over here, well, let's write this m2g, and let's write this as n2. So that is for number 2. For number 1, we'll have m1g, and the upward force would be the tension. Now, if it's accelerating to the right, we will have an acceleration in this direction, and this will have an acceleration in this direction. And this is the positive y. This is the x. So the acceleration will be in the positive y. Here the acceleration is in the positive x. So let's write the equations. Let's say first we write for m1. We have to write the equation separately for both of them. The tension and the sum of forces in the y direction equals m1 ay. This is going to accelerate upwards, so it's going to be t upwards minus m1g downwards. These are the two forces, and they equals m1 ay. So if tension is bigger than m1g, it's going to accelerate upwards. But if tension is less than m1g, m1g is bigger, it's going to accelerate downwards, and this will become negative. So with this assumption that it's accelerating upwards, we have this equation. Now we write the equation for m2, and first we write the sum of forces in the y direction, m2 ay. So, well, it's not accelerating in the y direction, it's only accelerating in the x direction, so this is 0. And the forces are n2 plus fy minus m2g, 2 plus and 1 minus, equals 0. Now, fy is going to be f sine theta, and therefore n2 is going to be m2g, well, it's not g2, g is always 9.8, m2g minus f sine theta. So we should be able to get the normal force here. And then the friction force here is mu k times n2, which is going to be whatever is mu, and well, n2 is from here. We solve this for here, and then we plug that in here and get the friction. Okay, so now we go to the x equation, and in the x direction we have fx to the right, tension to the left, minus f to the left. That equals m2 ax. Now the friction we have from here and fx is f cos theta. So knowing the f and the cos theta, we know fx. The tension is here from here, and friction is from here. So if I write this out, this becomes f cos theta minus tension, and tension is going to be m1 ay plus m1 g, that's T, minus friction, and friction is going to be mu times n, so it's mu k times n, and m2 is minus f sine theta. That's n2 times mu, so that's the friction, and the tension is from here, m1 plus m1g, m1a plus m1g, that's here, and that equals m2 ax. So now we should be given the force and the theta and the m's, and the g of course is known and the mu is known, so ay is the unknown. So we have one equation but we have two unknowns, and well, we know very well that this will be ax and this will be ay, and they will both be the same, so we really do not have to write ay and ax. This would just be a and a, so we could just erase that off. Okay, and now this equation we can get the value of a by some algebra, so that can be done. So to summarize the whole thing, let's just say that first make a diagram, a sketch of the problem, and then make a free body diagram, and then get force components if needed in x and y directions, and then solve the sum of force in the y direction equals may, and sum of forces in the x direction equals max, and then get the required answer for whatever is required. And one more thing, that is, whenever we have a pulley that is frictionless and massless, the tensions on both sides are equal. In a later chapter we will assume the pulley is not massless and the tension will no longer be equal. Then we'll have T1 and T2. So if pulley is massless and frictionless, then tension on both sides is equal to each other. Okay, and that helps us in solving these problems. One more thing that should be remembered is that the coefficient, just add it over here, that mu s and mu k are independent of the normal force and the area. They depend only on the nature of the two surfaces. That are in contact with each other. So if you press harder on this, if you press harder down here, it will increase the friction, but it will not increase the coefficient of friction. If you increase the weight of this object, it will increase the force of friction, but not the coefficient of friction. And if you have a three-dimensional object and you put it on the ground like this, there will be a certain amount of friction. If you lay this down so that it's a bigger surface is touching the floor, the friction remains the same if the coefficient of friction is the same, which is if the nature of the surface, side surface, is the same as the nature of the bottom surface, mu's will be the same, the normal force is the same, so the friction force will remain the same. So the area of contact does not matter. The weight does not matter. If it's an inclined plane, the friction will change, but not the coefficients. The coefficients do not change in this case either. The total force of friction will change. Okay, so that ends chapter 5.